Everyone. Thank you for joining us. I'm Martin Willis. We have another live stream session for the Scientific Coalition for UAP Research. Today's guest is astrophysicist Matthew Szydagis, and he'll be presenting on the possible connection between UAPs and dark matter. After his presentation, we will be taking questions from the chat, so be sure to get your questions in there. Now I will turn it over to Matt.
Thank you so much for that lovely introduction. Let's go right into my PowerPoint, if we can. So I am going to be talking to you about my work, my research into dark matter, which is an extremely broad field, lots of physicists in it. And in this field, you might think this has absolutely nothing to do with our main topic, which is the unidentified aerial phenomena. But I think what you'll find is there are a lot of intriguing potential connections. The more science I've done over the years, and I'm still, pretty junior scientist, pretty young still, I find that there's so much interconnection and also interdisciplinariness between different areas of science, between different areas of research. So I want to tell you a little bit, though, first about how I got interested in science. And like many fellow scientists, it was through science fiction first. It was primarily through Star Trek Next Generation and then Star Trek Voyager. And it was science fiction that was the hook that got me into real science, and yeah, these two shows were really captivated me, and I just wanted to say, in keeping with our topic of the potential, the question of can there be craft operated by beings from somewhere else, that it amazes me that given our latest research into exoplanets, which I'm not going to talk about, but my colleague, Professor Kevin Knuth, works on, is that Star Trek wasn't even optimistic enough of how many planets there are out there and how many potentially habitable planets. So in terms of real science, the three books that really influenced my thinking were The God Particle by Leon Lederman about the Higgs boson, Hyperspace by Michio Kaku, and Black Holes and Time Warps by Kip Thorne, who recently shared in the Nobel Prize for the discovery of gravitational waves with Ray Weiss and Barry Barish. So that kind of tells you a story of very briefly of me and where I come from in terms of what brought me into science in general. But now we're going to talk about, I don't have much time because I want to keep it, half an hour. So we have half an hour for questions. I want to get to the story of my title, What is Dark Matter? What does that have to do with anything? And the story of dark matter, unlike my story, begins many decades earlier. And it begins with several different physicists, and there's arguments, astronomers, and arguments about who was first. I don't want to get into, but in the 1930s, the Swiss astronomer Fritz Zwicky first found evidence that there was more mass than is visible in stars. But it was not taken seriously for many decades until really the pioneering work of Vera Rubin, who unfortunately passed away recently. Me and many of my colleagues hope she'd get the Nobel Prize or share in the Nobel Prize for dark matter someday. She recently passed away, unfortunately, but her work really took things to the next level. And so what does Vera Rubin's work look like? So she looked at the revolution of stars around centers of galaxies and found that instead of seeing them drop off like we would expect, as we see in our own solar system, for example, Pluto and Neptune orbit the sun at a lower rate than Mercury and Venus, and this drops as 1 over the square root of the distance. What we find instead is we see an increase, or we see an asymptote at higher radii, and this is true of the Milky Way, of Andromeda, of every galaxy that we look at. And we can also look at this a different way by looking at the X-ray emissions from gases in between galaxies. And so what we find is there's something binding clusters of galaxies together, not just stars within galaxies, but in between galaxies. There is additional gravitational force. And we're able to explain this by postulating a elliptical or spheroidal-like halo of invisible additional mass. Now, by itself, though, that is not at all the end of the story, since one could make the case that the galactic rotational data can be explained away. And very similar, I think there's a really good analogy between how when we explain away even the most compelling pieces of evidence of UAPs. There have been many ways to explain away this initial dark matter evidence by saying we just don't understand gravity. We don't understand the force of gravity, and we have to tweak Newton's equations or Einstein's. But that was only the one piece of data from the 70s, 80s, but now we have a lot more. We have, for example, gravitational lensing. So gravitational lensing is where gravity bends light. So you have a galaxy cluster that's incredibly massive. So you have this is a cluster of galaxies, each with hundreds of billions of stars. And there's this distant galaxy behind that cluster, not part of that cluster. And its image is distorted by the gravitational field of the cluster. So gravity on large cosmological scales can act like your glasses or contact lenses. Gravity actually can bend light. And that bending of light allows us to calculate how much matter is doing the bending. And those results were able to confirm the earlier work on revolution of stars around centers of galaxies. But even that, you might say, well, you could still modify the theory of gravity and say there's no such thing as dark matter. But there's more evidence that comes from something called the CMB, the cosmic microwave background. And the cosmic microwave background, I don't have time, one could spend hours on that topic alone, is basically the echo of the Big Bang, to put it simply. And it's a type of radiation that comes from all parts of the sky, coming from many billions of years ago, when the universe cooled down enough so that stable neutral atoms could form. And the fluctuations in the cosmic microwave background can be compared to models and allow us to pull out this pie chart, which is called the standard cosmological model. And in the standard cosmological model, we find that we can explain the CMB, we can also explain large-scale structure of galaxies and other astronomical observations if 25% of the universe is dark matter. It's some kind of form of matter that interacts primarily gravitationally or perhaps only gravitationally, with about 5% in atomic matter. So this 69% I'll also get to before the end. I don't work on dark energy, has nothing to do with dark matter, but it's very important to my topic today, actually. Even though I focus on dark matter in my research, I'm going to spend most of my time on dark matter. Towards the end of my talk, I'm going to touch on this mysterious 69% dark energy, which we know even less about. But one of the main points I want to make today is that I think it's the height of hubris to think that we're done with science and that we know everything. We already thought that once at the end of the 19th century, and we were very wrong. We understand about 5% of the universe. And to me, that is not a negative, actually. That's very positive. That means that we have so much more work to do, and that future generations of scientists have so much more to do to understand what is this and what is this 25% and what is this 69%. Now, you might think, 5% of the universe is what we understand. That's the periodic table. That's protons and neutrons. It's much worse than that, actually. So of that 5%, 3/4 is hydrogen and 1/4 is helium. So yeah, that adds up to 100%. So oxygen, carbon, all these elements necessary for life, biochemistry, are the sub 1% dregs of the universe that are produced as supernova remnants or neutron star collisions and are not produced in the Big Bang. So we actually, the elements that we care about, the hydrogen, oxygen to make water, carbon-based life, that can't even go on this chart. So that 5% atomic matter is mostly hydrogen and helium. So there's so much that we don't understand. There are all these tinier slivers here, like neutrinos, photons, black holes. So, back and forth, we always think maybe dark matter could be explained by black holes, but there don't seem to be enough of them with enough mass to get up to this 25%. So I should say also this pie chart agrees with everything I said earlier. So all these independent pieces of evidence all build on each other to form a coherent picture. So the large-scale structure of the universe also depends on dark matter. So dark matter interacts gravitationally, pulling in gas of the ordinary atomic matter, things like hydrogen and helium, to create this spindle web-like structure that we see in the universe. And these are simulations here, but then this is real data. Whoops. Pressed a few buttons too much. So this is real data from the Sloan Digital Sky Survey. So the cosmic web, we can explain with computer simulations the appearance of the cosmic web, as it's called, the structure, the large-scale structure of the universe, of clusters of galaxies and superclusters of galaxies. And I always tell my students this looks like the human brain. I don't know if that's something deep, one of God's jokes, a cosmic coincidence, but it's remarkable how the universe looks like a series of neurons and synapses. So, but what is that dark matter then? Okay, so we have all this evidence that it's not just modified gravity, but that we also need to see. I just got a text from my wife that the slides are not advancing. Martin, is that true?
Yes, I was trying to figure out a way to get a message to you. Yes, they're not. So let's remove it from the program and re-add it. There you go. It's working.
Okay. Well, that stinks. Okay. All right. So are they advancing now?
That one in particular advanced, it says historical perspective right now.
And now does it say revolution curves?
Nope. Maybe we're having a problem with it.
Dang.
Okay. Yes, it does.
No, but that's because I think it only works one at a time. What if I don't do full screen? What if I do this? Does this work now? Are you seeing different slides?
Yes, I am. Yep.
Okay, so now what I'm going to do, wow, okay, that's unfortunate. So I was really absorbed and I was full screen, so I didn't see anything. So I'm going to fast forward through the slides that nobody saw. People were probably like, what the heck chart am I talking about? All right, so here are the slides that you were supposed to see. So here's Picard and Voyager for how I get interested in science. Here's the books I read. Here's Wiki and Rubin. Here are the rotation curves from Rubin. Here are the dark matter halos. Here's the gravitational lensing slide. And here's the pie chart that I spent so much time talking about. 25% dark matter, 69% dark energy, 5% atomic matter. And here's what I was meant when I was talking about the cosmic web, which kind of looks like a human brain like structure. All right, so this is where I want it to be, slide 11. Okay, so I'll leave it. This seems to be working, so it's awkward since it's not full screen mode, but we'll leave it like that. So so I've talked about all the astronomical evidence for dark matter, but what is it? So we have a lot of different ideas that I won't have time to cover, but one of the ideas is called the WIMP, the weakly interacting massive particle. And the WIMP is kind of an umbrella term for multiple different ideas. And one of them is the idea that you have just analogous to matter and antimatter, you have what's called supersymmetry, where you have particles that are shadow particles of the known standard model particles, but at larger masses, actually. And the lightest of those superpartners could be a dark matter candidate. There are also other possibilities, like if there are extra dimensions, they might lead to there also being extra particles in a related way. There are also, besides WIMPs, other ideas like the axion particle, and these there are really no shortage of ideas. WIMP is sort of the standard default idea, but there are many. But since that's what I work on, I'm going to focus on the detection strategy for WIMPs. And I have this little cartoon I often use in my talk of an astronomer, and his wife shows him that he's looking in the wrong place for the comet. So hopefully we are looking, of course, in all the right places for dark matter. And our main detection strategy, called direct detection, is waiting for dark matter to come in and to impart energy to a nucleus. And what is that nucleus? There are many different elements that are used in the dark matter search. And in my own work, I work on an experiment called LUX and its successor LZ. And in these types of experiments, the idea is we use a large vat of liquid xenon underground in order to get away from all the naturally occurring radiation. And what happens is when we have this large vat of liquid xenon underground, and we have a particle come in, and that particle comes in and it hits a xenon nucleus, it produces a flash of light, but it also, which we record and call that the S1, but some electrons are also ionized and drifted to a small gas phase above the liquid, and they produce a second flash of light you see here in the video, and the time between the flashes gives us the depth of the event. And here's a picture of myself here with one of my former postdoctoral scholars and students, Jeremy Mock, in front of the titanium cryostat. So it's basically a giant thermos to keep the liquid xenon cold. So what do the results look like? So we have not found dark matter yet. We have not, despite decades of searching. Does that mean it's not there? No, because if you look at, for example, the field of gravitational waves that I mentioned earlier, it took decades of hard work to build the right experiment of the right scale to finally have success. So if the way experimental results are reported is you have this like parabolic like swoosh, a curve where you rule out models, and you rule out that dark matter has a certain interaction strength, probability of interaction. And so you basically make these curves here illustrated in orange, blue, and green lower and lower and lower. And that's a cartoon. So eventually the hope is that instead of having a line here, we draw a blob where we think we have seen a signal at a particular mass and interaction, a strength. So dark matter, by definition of being dark, we know that it doesn't interact electromagnetically. So that means it doesn't interact with light. So there is, the way we're looking for some kind of interaction with a nucleus in one of these detectors like LUX or its successor LZ. But there are more exotic dark matter models coming that abound now, as we haven't found the sort of default vanilla model from the 80s, where there could be more interesting interactions between a so-called dark sector, where instead of having one dark matter particle type that would be in one spot in this plot, there could be multiple kinds. And so one thing that I've been thinking about for a while is, what if there is a very small probability? What if it's not completely no probability of interaction with light or electromagnetic radiation? And it's a huge speculation and a complete wild guess, but I was pondering the possibility of whether some of the unexplained phenomena we've seen, like the famous Nimitz encounter video and discussion about the so-called tic-tac shaped craft, what if it's possible to have small, naturally occurring clumps of dark matter? It's a huge long shot, since, as I said, it's not supposed to interact with light and infrared is light. Radar is also a form of light. It's a form of electromagnetic radiation. So it's a bit of a long shot, but I wonder if maybe that is a more likelier explanation than a craft and piloted, intelligently piloted craft. So just throwing that out there. But that's all the time I have for dark matter. So for my last few slides, I'm switching gears to something else called dark energy. So dark energy is what governs it was discovered in 1999 that the expansion of the universe is accelerating. And so the name we've given for the cause of this phenomenon is called dark energy. And it's causing the universe, we don't know what it is, but it's causing the universe to accelerate. So it's kind of, in one sense of the word, it's kind of an opposite of dark matter, because dark matter through gravity, just like ordinary matter, is slowing the expansion of the universe, but dark energy is accelerating it. So how do we know that? So I talked to you, how do we know all this stuff? How do we think there's dark matter? How do we know this? So for dark energy, we use what's called type 1a supernova explosions. We use them as standard candles to measure distance and the expansion rate of the universe. But what is this dark energy? So our best idea, but it doesn't work. In fact, the calculation for this is orders of magnitude off, but our best idea is that the dark energy has something to do with what's called 0-point energy. And so I mentioned earlier the Nimitz encounter. I mentioned my colleague Professor Knut's work on exoplanets, and I have to tell you that it kind of sent shivers up my spine when I realized that the 0-point energy that for decades was like, oh, that's what the tinfoil, UFO crackpots are talking about. And then here we are, a Nobel Prize in 1999 for the discovery of dark energy, which probably is the 0-point energy. That's our best guess on what it is. And yet we would laugh at, here's this alleged alien abductee talking about 0-point energy. And here it is with real science. So that kind of creeped me out and made me think, you know what? Maybe there is, something to this after all. So I don't have enough time in the about 8 minutes roughly I have left here to launch into really deep explanations. So I can only give, just like I did with dark matter, a concise, short, simplified explanation of what these are. What does 0-point energy mean? Because that's thrown around a lot and incorrectly used very often, I have to emphasize. And so what we're talking about here is the fact that, and I say fact because we've demonstrated this with what's called the Casimir effect that's been measured, I've illustrated here, is that the so-called vacuum of space is not completely empty. What happens is that you have particle and antiparticle pairs that are constantly popping in and out of existence. Now, to be fair, though, if you talk to my colleagues in the scientific community, I heard both sides on whether these virtual particles that are responsible for what these so-called quantum vacuum fluctuations, are they real in the sense of, are they ontological, versus are they just a handy mathematical tool for calculation? And I've heard vehement arguments for both sides. But as an experimentalist, not a theorist, I can just tell you what can be measured. I mean, I have not done this myself. I'm a dark matter physicist, but the so-called Casimir effect has been measured, which is the fact that when you have two metallic plates in a vacuum, you can measure a force that develops between the plates even when you account and subtract out other effects like the van der Waals forces between the plates, things like that. And this effect comes from these virtual particles. It goes by many names. I'm using all these terms interchangeably, and they all have slightly different meanings, but they can be used almost interchangeably: 0-point energy, vacuum fluctuations. So I mentioned the tabletop tests we're doing for dark matter. They're not exactly tabletop. We have several tons of liquid xenon is the leading experiment, are used by leading experiments. For dark energy, it looks like the thing we do to look for it, even though it looks like it's some kind of related to some sort of tabletop thing. The primary technique for studying dark energy is astronomy with telescopes and looking at the recession velocities of galaxies. Nevertheless, recently, tabletop tests for certain specific types of dark energy have been developed. So there are certain tabletop tests that have been developed. I show an example here. There's a so-called chameleon dark energy. So let's tie that all together now. Tying in the dark energy with dark matter. And let's tie that all together. So my conclusion, in conclusion, about 95+% of the universe is unknown. So there's so much we do not understand. And I often joke with my students that there are dark matter aliens out there. I'm not saying that's likely because, again, dark matter doesn't interact very effectively, so probably wouldn't produce life. But I joke that there's a dark matter alien scientist out there trying to convince his or her alien government that they've solved the missing 5% of the universe, and they're going to call it the proton. And that's a two-sided joke because we laugh, I forgot about neutrons, electrons, and they're made of quarks. But actually, they wouldn't be that far off, since that 5% that makes up you and me is actually mostly hydrogen and helium. So it's mostly protons, some neutrons, but mostly protons. On the dark matter side, we're ruling out large swaths of parameter space. Now, the big takeaway, though, and the biggest connection that I have here with SCU and the UAP group is, I've been thinking about how if interstellar travel were real, either by us, by humanity, or by somebody else, could there be some way we could utilize the naturally occurring large energy densities of dark matter and dark energy? And that way, you're not violating any of the laws of physics, because I'm not saying some sort of momentumless propulsion. You would still be pulling in a fuel, essentially. But what if that fuel is everywhere, as part of the cosmos? Now, I have to emphasize, though, that's absurdly speculative on my part, because dark matter does not interact with anything. That's why we're having so much trouble detecting it in the first place. So how do we harness it, right? And even if you could harness it, what would the reaction be to make you go? So when we talk about things like Bussard ramjets, one gets nuclear fusion using hydrogen. With dark matter, I don't know if that would give you the oomph. That's not a scientific term, but impulse, I believe, would be a better term, right? But what would give you the oomph for the momentum transfer? Now, dark energy is a little more interesting beast there, because it's not a lot. It's not a lot, even though 69% of the pie chart. But when you break it down into energy per unit volume, it's really not that much. But if it's 69% of the universe everywhere, including our own galaxy, I'm thinking, what if, instead of dark matter, what if there was a way to somehow tap into that naturally occurring vacuum energy? And I by no means thought of that. There are countless papers, publications with different ideas on how to do that. So I by no means thought of that myself. There are countless different ideas on that range in plausibility and range in level of speculation. But I'm going to stop there, though, with 1 minute to spare. Well, I was told approximately 30 minutes. I think I hit 30 minutes pretty effectively, because I think it's time to switch to Q&A. So I think I'm going to stop my screen share there and hand it back over to you, Martin.
Yeah, sure. Well, let's see. We have some questions. Well, first of all, Robert wanted to know, will the PDF be shared?
Oh yeah, I would love to. So I'm not. I'll have to talk, I think, to Rich and Robert Powell. I see no reason why I couldn't be on the. We could put it on the SCU website. So I'll contact them after the show.
Great. All right. And so Robert Powell here has this question. There have been 2 small galaxies discovered that don't have dark matter. That's interesting. Does this mean their stars rotate more rapidly near the galaxy center?
That's an excellent question. So there have been, I didn't have time to cover that in my talk, so thank you for the question. What it means is that the stars rotate actually, it's going to seem counterintuitive. So as you go out to high radius, the stars actually rotate less rapidly. So but you're asking about near the galaxy center. I think near the galaxy centers is not much difference. I think the big difference is that as radius goes to infinity, so as you go away from the galaxy center, we see a reduction in velocity consistent with a Newtonian or Einsteinian curve. And I'm really glad you brought that up, Robert, because that's actually those discoveries. We don't understand how those galaxies are possible, by the way. I have to confess, we have no idea how that's possible. But the flip side of it is galaxies like that are strengthening the case that there is a mysterious dark matter, and that it's not a misunderstanding of gravity. Because these types of discoveries are showing us that there are some galaxies with more dark matter and some with less. We don't understand why, but that is implying that that dark matter is stuff and is not a misunderstanding in the law of gravity.
Excellent. Well, the next question also is from Robert Powell. If dark matter doesn't interact with light, would that also imply E equal mc squared does not apply to dark matter? Great question.
Yeah, I've never had that question before. No, I think E equals mc squared will still apply, and here's why. So there's a c, that's the speed of light in the equation, but you have to be very careful because the speed of light is not just about light, right? It's the speed of gravitational waves. It's the maximum speed of energy transfer in the universe. So just because an equation includes the lowercase c doesn't mean it has to do with light. So in the case of dark matter, here's where E equals mc squared would apply, possibly. Again, we haven't discovered dark matter yet, so I'm just giving you our best educated guess. But there's a type of dark matter detection I didn't get a chance to talk about called indirect detection. And an indirect detection, that's where you're looking for dark matter to meet with anti-dark matter and to annihilate, convert into energy. And then thanks to E equals mc squared, that energy E becomes new mass m. And you can get different particles. So one of the ways to look for dark matter is dark matter disappears, turns into energy. That energy turns into mass of new particles, and that is still governed by E equals mc squared.
Wow, my brain hurts after that answer. If dark matter doesn't interact with baryonic matter, how could we ever trap or harness it?
Yeah, great question. So yeah, these are all great questions. The idea is that in all of the dark matter searches we've been doing is that dark matter almost never interacts with baryonic matter, and there's an asterisk. And what is that asterisk? That asterisk depends on the nature of dark matter. So if dark matter is a supersymmetric particle or Kaluza-Klein or one of these other models, then there's a very, very, very low interaction rate with baryonic matter. But I should stress, it's entirely possible. It's a very depressing possibility, but it's absolutely possible that dark matter interacts with baryonic matter only through gravity and nothing else. If that's true, we will never harness it. We will never even directly detect it. That's a very depressing possibility, but as scientists, we have to acknowledge that possibility. And so there is a possibility that the interaction with baryonic matter is through gravity alone. Basically what I've shown already, that it pushes and pulls and it doesn't have any other interaction. But the idea is that in most models that predict a dark matter candidate, like supersymmetry that I mentioned, also predict that there's a teeny tiny, very weak non-gravitational interaction with baryonic matter. little window of hope.
Great. All right. Next question by Robert McGuire. Isn't 0-point energy and or virtual particles guaranteed by the Heisenberg's uncertainty principle?
The 0-point energy is, but virtual particles are another layer of interpretation that I think came after Heisenberg formulated his principle. But you're absolutely right that what I was discussing with dark energy that is intimately related with the Heisenberg uncertainty principle. But yeah, the idea of virtual particles don't, as far as I know, I'll have to double check. As a scientist, I'm unfortunately not also a historian, as science historians are a very important separate field. So I'm not 100% sure on this, but I don't think that I think the idea of virtual particles were in another layer that came long after Heisenberg originally formulated his principle. So that's why I think it's kind of separate and years later to take the idea of the uncertainty principle, which is governing real particles initially, and the energies of real particles allowing to fluctuate. We can then extrapolate that later after Heisenberg. We extrapolated that to borrowing energy from the vacuum also to create virtual particles.
Wow. Okay. Kevin Ganuth is asking, black holes are everyone's go-to for missing mass because they are black. As I recalled, they're ruled out as candidates by theory.
Well, it's more of a comment than a question, but that's okay. I'll forgive Kevin. But yeah, so black holes, I want to give you the most honest answer and to the whole audience. Black holes are ruled out and then ruled back in, and then there's just fighting. Okay, so within the community, dark matter community and scientific community, there's been back and forth on this, especially recently. So the idea that black holes could be dark matter, they work. On paper, they work, they fit the bill. Because they don't count as baryonic matter. They don't count as ordinary matter. Because once you're crushed into a singularity, you just interact gravitationally. But the issue is, the burning question are there enough black holes to explain the measured energy density of dark matter? We don't know what dark matter is, but we can measure the energy density. And the energy density, it's not clear whether there are A, enough black holes, and B, massive enough black holes, because it's about number, density, and mass. So I think it's an open question, but it's not very open, like you say in your last sentence there. It's pretty closed. It's fairly ruled out, but every so often you see another publication saying, wait, no, it's not ruled out. Maybe there are enough black holes. So I think it's an open question, but only a little bit. It's a mostly closed question. It's probably not black holes.
Excellent. Well, Kevin, again, inclined to suspect red M dwarfs to be better candidates. They are very dim and not visible at distances. That way, that they take up 75% of the stellar population. Can you rule M dwarfs out as candidates?
Yes. And here's the reason why. So they were already ruled out in the 1980s or 90s rather. And this was a counter to the dark matter. You know, we scientists, we love our jokes. So the opposite of WIMP was the macho. So you got WIMPs and you got machos. So M dwarfs count as something called a macho, which stands for massive compact halo object. The reason why they're ruled out is because even if there were enough of them, the problem is unlike black holes, they still act like baryonic matter. So what would happen is those M dwarfs, not just in our galaxy, but in other distant galaxies and all over the universe, would change the CMB. The cosmic microwave background would look different. So Kevin's right that my initial slides, my initial pieces of evidence for dark matter had no proof. There was no proof they're not regular matter. The key is the CMB, the cosmic microwave background, teaches us that dark matter is not baryonic. Because if it was made of protons, neutrons, and electrons like these M dwarfs, it would make a statistically significant difference in the fluctuations in the cosmic microwave background. So that's why it really can't be M dwarfs.
Great. Okay. Rich Hoffman here on this question. What would you need to test or detect if a UAP would have any relationship with dark matter?
Good question, Rich. So part of it is so lack of a propellant of obvious propulsion, to me, is already right now, that's a huge flag to me, that because I think that perhaps throwing out conservation of energy, throwing out conservation of momentum is kind of extreme. We can explain propellantless propulsion within the known laws of physics if you do have a propellant that you just can't see. And so that's my best answer, I think, is that when you have something capable of moving at incredible speeds and potentially through space without an obvious propellant, I'm more inclined, and I know there's an Occam's razor potential disagreement there, I'm more inclined to say, no, conservation of energy and conservation of momentum still work. If they didn't, this computer wouldn't work, your phone wouldn't work, all of our science and technology wouldn't work. So I'm thinking maybe momentum and energy are still conserved even by advanced technologies, but there's an invisible propellant that's invisible to our current sensors and detectors.
All right. Kevin's got another one here. Do you want to say anything about metamaterials and resonances with the bismuth magnesium samples?
Yes, I do. Thanks, Kevin, for that question. But for those who don't know in the audience what Kevin's talking about, so there have been, well, I'm sure in this audience, actually, I bet the vast majority do know what he's talking about. There have allegedly been crashes of craft with mysterious materials that do seem to be beyond our current technology. So and there are so many, there are articles, there are YouTube videos on this material. And one thing that really made me very interested, I should have had a slide on this actually, thanks Kevin, but again, I wanted to keep it to 30 minutes. One thing that really creeped me out, and I think this is why Kevin asked this question, so I'd bring this up, is the paper I referenced in my talk, which, as I said earlier, I'll share publicly. There's nothing private, secret there. So I referenced this talk about tabletop tests for dark energy. And this, again, to be a good scientist, I have to be skeptical, and this could be a complete coincidence. But what really creeped me out is that the size scales that they were testing for these tabletop dark energy matches the alleged scales of these metamaterials. And so one might be inclined to make the conceptual leap that maybe one could use metamaterials in some way to channel this one form of dark energy, chameleon dark energy. Again, there's a lot of steps there, and it's a big conceptual leap, and that's a huge speculation, but it really got me excited when I sat down and compared the alleged specs of these alleged samples with the tabletop tests being done for chameleon dark energy. The agreement just scared me, just blew me out of the water, because I don't like coincidences. I don't believe in that level of coincidence.
Okay. Let's see. Paul wanted to know any thoughts on your UAP/UFO trace evidence cases, and have they ever interested you?
Oh, yes. Thank you so much for your question, Paul. So again, to try to compress my talk into 30 minutes, I could have had an additional slide telling you that one of the other things that interested me in science and made me become a scientist is not just Star Trek and then those books by Michio Kaku and Kip Thorne. I've got, from childhood, I have a giant library of UFO this and UFO that. And the trace evidence cases, I could quote you them forwards and back. And there's the there's the Lonnie Zamora case, and there were people who went and took physical evidence. There was oh damn, I just bragged about how I remember, and I can't remember the name. There was a case in Texas. I'm blanking on the name, but the diamond-shaped craft, the Cash Landrum case. People got cancer from alleged exposure. There's physical evidence, and so I've always thought that as scientists, like I said, we have to be skeptical. But there's skeptical, and then there's another level of skeptical where I shove evidence in your face and you still say, no, not going to look at it. No, I don't believe it. And so I really like your question. I have found these cases personally very compelling, and that I think that they're ignored by the majority of the scientific community. And I think part of the reason why is because the cases you mentioned are kind of, and obviously that's a matter of debate, are very few and far between compared to hoaxes or misunderstanding what you're seeing. And so there's that tiny sliver of cases that you're not going to make go away that are very, very difficult to explain away with natural causes. And I find those extremely compelling. And I don't think they should be ignored. I think they should be followed up on more.
Excellent. Great. Robert has a question here. What caused your interest in UAPs?
So first it came from, first it was cultural. Since, as I mentioned earlier, since I grew up watching Star Trek, I thought, oh, of course there are alien races and we'll find them someday. That's just normal. So first it was from fiction, acculturation, but then there was a second level. Because then it disappeared, because, as I just mentioned in answering the previous question, it's not taken seriously by the scientific community. So then I worked on dark matter, which is ironic, because by some other members of the scientific community, like I know a lot of chemists and engineer friends who are like, yeah, that's dark matter's nonsense. But I work on dark matter. I forgot about UAPs. But what brought a second wave of interest to me as an adult in a professional career, and not just in childhood, is actually the discoveries in the field of exoplanets, which my colleague, as you know, Professor Kevin Knuth, who asked several earlier questions, works in. It amazes me that how can we sit here and say, oh, alien visitors, that's a stupid idea, that's unlikely, that's extraordinary, that requires extraordinary evidence. I'm going to turn that around. I'm sorry, but it requires extraordinary evidence for you to convince me we're alone. In the Milky Way galaxy alone, there are probably trillions of planets, trillions, okay, because we've only found 8,000. In a little tiny patch of sky, we have found 8,000 or 4,000, whatever. Kevin has the right number. But extrapolate that to the Milky Way. There's nothing special about the point of sky we picked. Extrapolate that, trillions of exoplanets, okay? That doesn't count moons. What about exomoons? So what caused my interest in UAPs is the fact that we need to revisit our assumptions, I think, as humanity and as a scientific community. We think, oh, alien visitors, ha ha, that's so dumb. But why would we laugh and say it's so dumb? Because we used to think this was the only solar system, it was the only one we knew about. And now we've discovered thousands of planets, thousands of solar systems. And according to my colleague, Kevin, we estimate, huge error bars I know on this estimate, we estimate about 20% of exoplanets in the Milky Way are probably in the habitable zone. So that means they probably have liquid water. And that's only for our kind of life. What about other kind of life? So to me, what caused my interest? My interest is caused by the fact that our assumptions that we've been making for decades, that this topic is not interesting, were based on incorrect, flawed assumptions that were then disproven by astronomers who have found no shortage of planets. And so now you're going to have to claim that life emerging is very rare. But even if you take a rare number, you take a small number, multiply it by a huge number, we may still have compelling evidence that we are very, very unlikely to be alone. And the other thing, I've already answered this question for too long, so I'll make it quick. One more sentence is that the other thing that caused my interest is the realization when I learned Einstein's theory of relativity, that another false assumption that's been made for decades. Oh, we can't, interstellar travel is impossible, it'll take too long, it would take too long, it would take thousands of years. If you travel near the speed of light, time warps. And that's not a hypothesis, it's a scientific fact. We do it every day. Your GPS wouldn't work without accounting for this. So when you go at high speed, if you go close to the speed of light, so that means, my colleague Kevin has beautiful animation and slides showing this. You can cross the galaxy in a few months. It's not a question of physics, it's a question of engineering. So my interest in UAPs was sparked by discovering that two assumptions were wrong. One, that interstellar travel takes a long time. No, it doesn't. Not in the ship frame. Not if you have fuel that allows you to move near the speed of light. And second of all, the assumption that our solar system is unique and Earth is unique has been brought under serious assault by discoveries in the field of exoplanets.
Well, I got to say, I've asked that question personally a number of times. That's the best answer I've ever heard. That's really great.
Thank you. I appreciate that.
Yeah. Okay. Krang has, if you could get any question answered by an alien on board these UAPs, that's an opinion. What would it be?
That's an outstanding question. So again, as a scientist, I have to be skeptical, but I'm not as skeptical as in the extreme. So I'm open to the possibility. But I'm not going to say that, for sure, every UAP is an alien craft. But let's say it is. Let's say that at least some are. What I would ask, I already did this by email a few months ago. Kevin will remember this. I wrote a series of questions, and the first one that came to my mind is what is dark matter? So if they're so advanced, even if they don't use it as fuel or whatever, like I suggested, they should know what it is. And the answer to that question is so technical that it immediately tells me whether we be dealing with, for example, a hoax put on by humans versus an actual alien. I would want to know the mass and the cross section. And if there is no dark matter, if I'm wrong and it's modified, okay, then how do we modify gravity to explain away the observations, to show me the equations in Einstein's theory of general relativity? Where is this wrong? Show me where is this wrong that explains away dark matter. That would be my number one question. Because even an intelligent human who works in dark matter would have a tough time hoaxing a good answer to that question.
Great. So Errol has this question. Have you given up on detecting WIMPs? And if not, what's the next step?
Great question, Errol. So we have not given up. Something you have to keep in mind in terms of scale also is that even our biggest dark matter experiments are a tiny taxpayer expense and a tiny cost compared to missiles and wars, for example. So if we had the same budget as like the Defense Department, if the DOE or NSF had a similar budget, oh my God, probably would have discovered dark matter long ago. So what's the next step? So what's holding us back is dark matter. It looks like it probably interacts more rarely than we thought, which means we need, unfortunately, to build a bigger instrument. So the current experiment I work on is called Lux Zeppelin. It's the sequel to Lux. It's a bigger device. Does that mean we'll just keep building bigger and bigger to infinity and never give up? No, because we're also building smarter. We learned from the previous stage experiments. And we also are not giving up yet because we still have some models like Higgs boson mediated WIMPs and supersymmetry that are not quite dead yet. Now, that being said, there is potentially a natural endpoint, which in 10 or 20 years, we may hit what's called the solar neutrino floor, in which case neutrinos from the sun might overwhelm a dark matter signal, so that even if dark matter is there, it might be forever beyond our reach. So we kind of have a natural endpoint, although even that's arguable because we're clever and we might find a way to keep looking beyond that. But there are all kinds of things besides WIMPs. There's WIMPzillas, there's SIMPs, there's elders, there's axions. There's no shortage of ideas. Because I'm an experimentalist, though not a theorist, I can't judge which are more compelling than others. So as an experimental physicist, I have to listen to what theoretical physicists and phenomenologists are saying as what's hot. And WIMPs are not dead yet. So I could probably quote, Mark Twain for you, but their death has been greatly exaggerated. There's still compelling parameter space that has not been ruled out yet. But thank you for your question.
All right. So Zachary asks about the galaxy's missing dark matter. Is uniform distribution of dark matter expected by theories or not? He later below writes he's basically wondering if there's anything unnatural about missing dark matter.
So great question. So twofold answer. So is the uniform distribution expected? No. So it is expected to be clumpy. And the question is, we don't know the scale of the clumpiness because there are different computer models and simulations. So we do expect clumpiness. But the second half of your question, galaxies without dark matter, are those unnatural? The answer is yes. So let me explain how the answer can be yes to both. So we expect clumpiness. However, the way we think it's supposed to work is that you first get a clump of dark matter, and that attracts ordinary matter. And then that's how you get, stars, galaxies, how you get star clusters, how you get a formation of a galaxy. So the honest answer, and regardless of how we've been taught science in elementary school, science is not about memorizing facts. It's also being honest about what you don't know yet. The asterisk is yet. So we don't know yet what the heck would cause a dark matter, a galaxy without dark matter. So to answer your second question, it isn't natural. No, it's not natural. So it is weird, and it is trying to tell us something we don't know yet. So that's one of those things we do not know the answer to yet that's going to require more study.
Excellent. Okay, Robert Powell again. Probably the most common electromagnetic connection with UAPs has been in the microwave band. Any thoughts on this related to dark matter?
Good question again, Robert. I'd have to look at some of the numbers and think about it. It depends. There's so many different dark matter theories and models. There's WIMPs, there's axions. So the first thing that pops into my head is I know that the axion particle, another dark matter candidate, but also an interesting particle separate from dark matter, that there have been searches in the microwave and RF region. I showed a microwave cavity, actually. Again, though, we run into the same problem of the rarity of interaction with the electromagnetic force. Again, not zero, but extreme rarity. But the first thing that popped into my mind is that the axion particle might be related to microwave or RF frequencies, and that is another different candidate, speculative particle in its own right.
Very good. Another question from Kevin. What is the probability that astrophysics would have predicted life?
0. So I often tell my students that it amazes me how, we talk about how hard physics is. And so freshmen will do biology first, which is backwards, I think, in high school. But it amazes me how hard biology and medicine is. I mean, coronavirus proves this, and how easy physics is in some ways. Physics is easy. I know you're going to say, physics is easy. Am I crazy? So, but I can write an equation down. It's called the Friedman-Robertson-Lemaitre-Walker metric, that I can write down in one line an equation that governs the expansion of the entire universe. Now, try to write down one equation that governs the human body or any living being. So I think there are a lot of emergent properties and complexity that are not at all covered in astrophysics. So as a physicist, I've made fun of my colleagues in biology, and they'll tell you chemistry. I'm like, oh, that's just applied physics, and physics is much harder. But I also have to give them some respect for the fact that biology and medicine, in some ways, is way the hell harder than some aspects of physics, especially astrophysics, where we can write down some simple equations. We can run computer simulations of the entire universe. I showed you one earlier, but it went by really fast. That might have been when my slides weren't advancing. But show me a simulation of the entire human body. We can't do it. We can't do it. We don't have a simulation to test drugs, to be able to will this drug kill someone? Instead of doing an FDA trial, I wish we could just pull up our computer and be like, okay, simulate human being with heart problem. We can't do it, even with modern supercomputers. So I think in that sense, if you just look at the universe, I would say you cannot infer life, especially not intelligent life, just looking at astrophysics and cosmology.
Oh, I do want to comment here. I want to say thank you, everyone, for your great questions that have been rolling in. We're right up on the hour, but we're going to go. We have a couple more questions left. Are you familiar, this is from Jonathan Lace, are you familiar with any of the papers dealing with dark energy from ATIP? In example, warp drive, dark energy, and manipulation of extra dimensions?
Yes, absolutely. In fact, when I mentioned earlier in my answer to Kevin about the metamaterials and dark energy scales, when I discovered that calculations seemed to match, I immediately emailed Hal Puthoff, and I'm like, maybe this could be connected. So yeah, I am familiar. I'm not going to say very familiar, but since dark matter is my main thing, not dark energy, but I have looked with great interest at the existing body of work in that area, and I have a suspicion. That maybe we are onto something there.
Interesting. Here's a fun question from Robert Powell. If you could have dinner with anyone who is no longer alive, who would that be and why?
That's a really hard question. I can't just pick one. The problem is there's so many things bubbling up in my head. So the obvious one is Albert Einstein. So I'm trying to stay away from that because that's obviously every physicist would say that. The other two names that are popping up on my head are Leonardo da Vinci and Galileo, because maybe they were centuries before us. And so, okay, they didn't have the benefit of quantum mechanics and relativity. However, especially Da Vinci, was a truly interdisciplinary individual who really thought about science and technology from so many different angles. I've got one that trumps all of those. It just popped in my head. And Kevin will love this. Giordano Bruno, who was burned at the stake for saying that there are other Earths and other planets. I'd love to talk to him and be like, you know what? Guess what? You were right. We haven't found conclusive evidence of aliens yet, but guess what? You were right. There are thousands of other planets, possibly trillions. So actually, I think I'll go with Giordano Bruno, and Kevin could join us. Kevin Knuth could join us too.
Great answer. Okay, the last question here from Zachary Russell. Thanks again for the answers. I wonder, and this is kind of a statement here, I wonder if discovering odd things about dark matter elsewhere could be the avenue for SETI. Could be an avenue for SETI.
I'd never thought of that before. I guess this connects with Zachary's earlier question. If there was a civilization that could manipulate dark matter, maybe that would explain why there are some galaxies without it, because they depleted it. Maybe it's a natural resource for them. I'd never thought of that before. That's quite an intriguing kind of left field, but very intriguing idea. Because I guess if you had an advanced civilization that could manipulate dark matter, maybe that would create unnatural densities, under densities like we've seen in over densities. Yeah, I've never thought of that before. Very interesting.
Wow. And by the way, Kevin says he would be glad to join you for dinner. Count him in. So that's it for questions. Thank you so much. That was really great. That was really great. And let's see. That's it for the show then, right? So I want to thank everyone for watching, and thanks for joining us at this live stream. Please hit the subscribe button below to be alerted for our future live stream events. We plan to have them at least once a month, and they are all featured scientific topics related to unidentified aerial phenomena. You can also visit explorers.org for more information. And thank you again, and we'll see you next time.